So what I now want to take a chance to talk about is what's called average value or mean value. Uh, One thing to watch for is this is not average rate of change. So we really have to watch for those words. So if we're being asked for an average value or the average of a function or an average temperature or an average cost, those are not rates of change. If we want an average rate of change, we are very specifically told average rate of change. But an average value is something different. If we think in this in terms of grades, you find an average grade by adding up how many grades you have and dividing by the number of them. Uh, and this is true as long as your data is what's called discrete. When you have test grades or homework grades in a class, those grades are discrete because a 97 on one test and say an 85 on a homework, you don't hit every grade in between those. They're their own separate data points. But if we think in terms of, say, gasoline that's being pumped at a gas pump, going from 8 gallons to 9 gallons is a continuous act, and you have a continuous amount of data in between the 8 and the 9 gallons. That would be continuous data, not discrete. So when we're dealing with discrete data, it's fine, but things like measuring gasoline or temperature even, where it's actually continuous data, we need to approach average value a little bit differently. But it's still the same idea. We want to add up or accumulate all of the y values. And that's actually what the integral does for this, is this accumulates the f values. But since we technically have an infinite number of them, instead of saying divide by how many, it's more of divide by the width of the domain in which we're looking at. But it's still thinking in terms of divide by how many. So the average value, and that's what AV stands for, average value of the function is 1 over b minus a, which are the endpoints of our domain, times the integral from a to b of our function, and that integral accumulates the f values from a to b on that domain. And this gives us our average value. So as an example, if I wanted to find the average value of 4 minus x squared on the closed interval 0 to 3, well, the way we do this is we want to find the average value of f. So it's 1 over the distance between my endpoints here in the domain, so 1 over 3 minus 0, times the integral from 0 to 3 of our function with respect to x. Well, 1 over 3 minus 0 is pretty easy. That's 1 over 3. This integral, which there are multiple ways to calculate, one being on your calculator, but no matter how we calculate it, we get 3. 1/3 times 3 is 1. So for 4 minus x squared, between 0 and 3, it has an average value of 1. Now, one consequence of this is that we can actually adjust our mean value theorem. And it's going to be in a few videos before we discuss why we can make this adjustment. But there's actually a mean value theorem for definite integrals, which says if a function is integrable on the closed interval a to b, then there exists some point c somewhere in there. So somewhere in that interval where f of c is equal to 1 over b minus a times the integral from a to b of that function. What it really is saying is that if a function is integrable on a closed domain, then somewhere in that interval, the function itself will equal the average value. And that's similar to what we did when we were doing just the MVT, which says that if a function is continuous on a closed domain and differentiable on the open domain, then somewhere the instantaneous rate of change must equal the average rate of change. So this is saying that if it's integrable somewhere, the function's actual y value has to equal the average y value.